Welcome back. Before we start our deep dive into today's topic, please take a second to hit that like button, subscribe to the channel, and turn on notifications so you never miss a technical breakdown. It really helps the channel grow. Welcome to this deep dive into Apache Storm, the powerhouse behind real-time stream processing. Storm is designed to handle massive volumes of data in motion, ensuring each event is processed reliably and at scale. Unlike batch processing systems like Hadoop, Storm operates continuously, making it perfect for applications requiring instant insights. So why choose Apache Storm? It excels in environments where speed matters. Whether you're monitoring live transactions or tracking social media trends, Storm delivers sub-second latency with guaranteed message processing. Its extensible API allows developers to build complex topologies in any language, making it versatile and powerful. Before diving deeper, let's understand the core concepts. A topology is a network of spouts and bolts connected by streams. Spouts generate data, while bolts process it. Everything revolves around tuples, the basic unit of data in Storm. These components work together to form a real-time processing pipeline. Apache Storm's architecture is distributed and resilient. At the top is Nimbus, the master node that distributes code and manages assignments. Supervisors run on worker nodes and execute the assigned tasks. Zookeeper acts as the backbone, coordinating the cluster and maintaining state. Together, they ensure high availability and fault tolerance. A topology in Storm is essentially a DAG, a directed acyclic graph of spouts and bolts. Spouts emit streams of tuples, which flow into bolts for processing. Each component can be parallelized, allowing Storm to scale horizontally across multiple nodes. This modular structure makes topologies flexible and efficient. Spouts are the entry point of data in Storm. They generate streams of tuples, which are then consumed by bolts. Spouts can be reliable, meaning they replay failed tuples, or unreliable for performance-critical scenarios. Common sources include Kafka, message queues, and even simple file readers. Bolts are the workhorses of Storm. They process incoming tuples, applying logic like filtering, aggregation, or even joining data streams. You can chain bolts together to build complex processing pipelines. Each bolt can emit new tuples, allowing for multi-stage transformations. The lifecycle of a tuple in Storm begins at a spout and flows through a series of bolts. Each step can acknowledge or fail the tuple, enabling Storm's fault-tolerant behavior. Anchoring allows tuples to be tracked, ensuring they are reprocessed if failures occur. Fault tolerance is one of Storm's strongest features. Through tuple anchoring, Storm tracks each tuple's path. If a tuple fails to process, it's automatically replayed. Failed tasks are restarted by supervisors, ensuring no data is lost. This mechanism guarantees at least once processing semantics. In terms of performance, Storm is a beast. Benchmarks show it can process over 1 million tuples per second per node, with sub-second latencies in most cases. Its horizontal scalability ensures you can grow your cluster as demand increases, making it ideal for high-throughput applications. How does Storm stack up against other stream processors? Compared to Flink and Spark streaming, Storm offers the lowest latency and highest throughput for real-time use cases. While Flink excels in stateful processing, Storm remains the go-to for pure speed and simplicity. One of Storm's unique strengths is its language-agnostic design. While built in Java, it supports integration with Python, Ruby, and other languages via its multi-lang protocol. This makes it easy to incorporate into existing systems, regardless of the tech stack. Let's look at a real-world use case: real-time analytics. Imagine processing data from sensors, logs, or user events in real time. Storm topologies ingest and process this data, feeding results into dashboards or BI tools. This enables businesses to make decisions instantly based on live insights. Another powerful use case is fraud detection. Storm can process transaction streams in real time, applying machine learning models to detect anomalies. Suspicious activity is flagged instantly, triggering alerts or even blocking transactions before they are completed. In the world of IoT, Storm shines in monitoring sensor data. It can detect failures or anomalies instantly, alerting operators for maintenance. This proactive approach helps optimize resource usage and prevent costly downtime. Storm supports multiple deployment models. For development, you can run it in standalone mode. In production, it's typically deployed in cluster mode, often integrated with orchestration tools like Kubernetes. Scaling is straightforward, just add more worker nodes. A common integration is with Apache Kafka. Kafka acts as a spout source, feeding real-time messages into Storm topologies. This combination provides a scalable, fault-tolerant pipeline for ingesting and processing large volumes of data. It's important to distinguish Storm from Hadoop. While Hadoop excels in batch processing, Storm handles real-time streams. They're complementary. Many organizations use both to build hybrid workflows that process data in real time and in batches. Ready to try Storm locally? Download it from the Apache website, extract the files, and configure Nimbus and Supervisor. Start the services and deploy your first topology to see real-time processing in action. Setting up a Storm cluster involves installing Zookeeper, configuring Nimbus and Supervisors, and deploying topologies across nodes. Once running, you can monitor performance and health using Storm UI or external tools. Monitoring and debugging are crucial for production use. Storm UI provides real-time topology insights, while logs help debug issues. Metrics give performance visibility, and alerting ensures failures are caught early. Storm UI is a powerful tool for visualizing topologies, tracking component metrics, and identifying bottlenecks. It's essential for optimizing performance and debugging issues in real time. To get the most out of Storm, follow best practices. Minimize tuple serialization, use field grouping for efficient routing, balance parallelism, and monitor resource usage to avoid bottlenecks. Avoid common pitfalls like overloading bolts, ignoring tuple anchoring, or misallocating resources. Always use backpressure to prevent system overload and ensure smooth operation. Scaling Storm is straightforward. Add more supervisors, increase bolt parallelism, or integrate with resource managers like Yarn. Always monitor for performance degradation to ensure optimal scaling. Security is critical in production. Enable authentication, use TLS for communication, implement role-based access, and maintain audit logs for compliance. These steps protect your data and infrastructure. Looking ahead, Storm is evolving. Expect better cloud-native integrations, improved stateful processing, and enhanced support for microservices. These updates will keep Storm competitive in the stream processing space. Join the Storm community. The official website, GitHub, and forums are great places to find resources, contribute, and get help. Don't forget to check out the documentation and tutorials for deeper insights. Let's recap Storm's key features: real-time processing, fault tolerance, scalability, and language flexibility. Its seamless integration with tools like Kafka makes it a top choice for modern data architectures. Apache Storm is a robust solution for real-time data processing. Whether you're building analytics dashboards, fraud detection systems, or IoT monitoring tools, Storm provides the speed, reliability, and scalability you need. Thanks for watching this deep dive into Apache Storm. If you found this helpful, hit that like button, subscribe for more content, and let us know your favorite use case in the comments below. And that wraps up our explanation. If you found this useful, please hit the like button and share it with a fellow developer. Don't forget to subscribe for more technical tutorials. Thanks for watching, and I'll see you in the next one.